So that's exercise 4.17. Says to find the value of diode small signal resistance at bias currents of 0.1, 1 and 10 milliamp. So just employ the basic relationship, which was that RD is equal to threshold voltage divided by the diode current, and we know VT is 25 millivolt at 20 degrees Celsius room temperature. So for all three values, we will just plug in these values. 25 milli, we'll put 10 raised to power minus 3, and 0.1 milliamp, we get 250 ohms. And similar way for the second value, we would get same 25 divided by 1. Remember, I'm not plugging in the units here. This is millivolt, this is milliamp, again this is millivolt, and this is milliamp, and the resistance of small signal diode resistance then changes accordingly. So same for the third case. For the 10 milliamp, we would have 2.5 ohms. So many times we need this value to find other parameters of our resistance. So let's take a look at another example where we are given a circuit and we are given the output voltage 3 volts, and the load current is 0, and output voltage changes by 20 millivolt per 1 milliamp of load current. So that's for small signal. We have to find the output resistance, which is the resistance that we would be looking from this side, and that's function of the output voltage and the load current. So this is for the small signal analysis. So this is 20 millivolt, and this is changing for 1 milliamp of the load current. So this gives us a value of 20 ohms. So total small signal resistance of these 4 diodes is then 20 ohms. Now for each diode, then we have to divide this into 4 for 4 diodes. So we can then get RD as 5 ohms. Just divide this by 4 and we get 5 ohms. Now we go back to the original relationship for RD. RD is the threshold voltage divided by ID. So which in this case, if I take my ID value of 5 here, I can find my diode current. So that's 25 millivolt divided by ID, and that gives us the diode current of 5 milliamps. Now, what's the resistance now for this circuit? So again, voltage divider, and as we talked about analysis, for our small signal analysis, we take it as a ground. So this is now a voltage divider where we are seeing this guy and resistance from this guy and this guy. So we need to find out what should be the R value here. And that's the question. So R would be then the difference of voltage divided by 5 milliamp. So that's 2.4 kilo ohms. Right. So now the second question, part B, is that specify the value of IS of each of the diode. Now we go back to the basic fundamental relationship for the diode current, and that was the diode current is an exponential factor of the basic current V over Vt. So by rearranging, we can write down Is to be a function of Id divided by the exponential goes to the other side. I can directly write it as e to the power minus, but let's just stick to the way it is, V over Vt. And that would, so let's just plug in the values. So we have Id is 5 milliamp. We just calculated that. And e to the power, the voltage we are using here for the second question is 0.7 for the turning it on divided by the threshold, which is 0.025, 25 milliamp. So that gives us the current as 10 raised to power minus 16 amp. All right, so that's the IS. Now the third one. For this design, use the diode exponential model to determine the actual change in output voltage when a load current of 1 milliamp is drawn from the regulator. So this word regulator, we'll just get into that. The idea is that this network of diodes results into a regulated voltage at the output terminal. Now, the current that's going through diode is the difference of the current that's flowing minus the load current. And that gives us 4 milliamps. Remember, we found our diode current as 5 milliamp here. So we are just using that here. Now, across each diode, the voltage drop can be found by using the same relationship, but now we will bring things on this side. So we'll rearrange to find the diode voltage. It would be Vt log of Id over Is. So because we are using the exponential model here. So when we plug in the values, we get the diode voltage to be 0.7443 volt. We know this guy, and we just calculated this in part B. So now this is the voltage drop across 4 diodes, right? Oh, this is the voltage drop across one diode. So across 4 diodes, this would be 4 times, which is about 0.75, 7428, so about 2.9, something around 2.977 volts. So if you look at it, the question took us from the output voltage of 3 volts to finding how would this change if the current changes from 0 to 1 milliamp. So the difference then is between 3 minus 2.977. That's the answer, and that's 23 millivolt for the change in the output voltage. We looked at the operation in forward bias and reverse bias. So the almost constant voltage drop, which happens in the reverse bias, or what we call at the breakdown voltage, that can be used for amplification and use it to maintain nearly constant DC voltage also. So these are called voltage regulators. There are two reverse breakdown mechanisms that cause this breakdown to occur in reverse bias. One is called avalanche breakdown, and that happens at typical breakdown voltages of uh, greater than or equal to 10 volts in reverse bias. It's a common form for reverse breakdown when we had to withstand a high reverse voltage without any appreciable current. So once we get into avalanche breakdown, so the large reverse current at the high breakdown voltage results in very high power dissipation. So we have to have circuits that do not let it get to that limits, because that would result in overheating and permanent damage to the diode. So we, in many applications, we avoid avalanche breakdown, and we just keep it within the uh, a limitation. We put a maximum limitation on that. So and this is just showing breakdown generally, but a breakdown that we are interested in and that we use a lot to operate in what we call Zener breakdown, or we call these as Zener diodes. So what they do is they give us a nearly constant reverse voltage drop. We call it VZ, and this VZ is what can be adjusted over a broad range. So depending on the diode we are using, there will be different values of VZ related to a Zener diode. And now it's reverse bias, so the current flows into the cathode, and cathode is positive with respect to anode, as we can see in this case also. And current and voltage, so Zener current and Zener voltage both have positive values. Now for currents that are greater than what we call the knee Zener current, we use IV characteristics, which are, we take that just a straight line. So if you see, if you zoom into this part, this is just a straight line with a slope RZ. So Zener resistance. So in this case, now we are talking about resistance related to the Zener diode. Now, and we specify them accordingly. So if we have a 6.8 volt Zener diode, that would mean that at 6.8 volt drop at a specified test will give a current of say 10 milliamps. So we know exactly what would be the ranges in which they would be operating. So as the current through the Zener, if it changes from a value, that would result into a relationship which would result into the Zener voltage change also by some signal. So let's say if the current is changing by delta I, then we would have the voltage changing by delta V. This is a very important relationship, because here what we are using is RZ, which is the slope of the almost linear IV curve at the Q point. So our RZ will come from the slope, and we call this resistance RZ as the incremental resistance at operating point Q. We also call it dynamic resistance of the Zener diode, and this is given by the manufacturer on the data sheet. And this can range from few ohms to a few tens of ohms. Now, it is obvious that the lower is the value of RZ, the more constant the Zener voltage will remain, as is its current will vary. And it will be more ideal in its performance with respect to its use as a voltage regulator. And if you can, we can see here the voltage regulator idea is that the current fluctuation is not changing the voltage too much. The current is dramatically changing across a big range, but our voltage change is very small according to that. So that voltage across a Zener diode is of our interest in voltage regulators. So our circuit in parallel to the Zener diode would see very small change in the voltage, and hence the concept of voltage regulator. Now, Zener diodes are made with the voltage VZ in the range of a few volts to a few hundred volts. And in addition to specifying the Zener voltage at a Zener current, RZ and IZK, the manufacturer also tells what's the maximum power that it can safely dissipate. So we don't want to take it too high in current because that would result into device physically getting bad and burning. So half a watt 6.8 volt Zener diode can operate to a maximum current of about 70 milliamps. So now the almost linear behavior in this region tells us that the device can be modeled like it is shown here. And here VZ naught or VZ0 denotes the point at which the straight line of the slope, which is here 1 over RZ, that intersects the voltage axis. So if you would extend this line instead of turning, sorry, this line, this is the point where it will hit the voltage point on the voltage axis. So VZ naught is shown here to be slightly different from the knee voltage VZK, but practically they are almost equal. So this value tells us another thing, that if I make equivalent circuit model of this guy, I can write it in a way, this is just a bigger picture of the same thing. I can write it in a way where my Zener voltage is composed of VZ naught plus RZ IZ plus the voltage drop that is actually happening around the Zener diode. So this is the equivalent circuit that can be described for this. So all what we are doing is we are adding the voltage drops across this loop, and here we have another observation that the IZ is is greater than IZK. So when we are given the knee Zener current, we'll see that that's way bigger than the current value which is at this point versus any other point for the Zener diode. And obviously the VZ is much greater than VZ naught or VZ output, right? So because that's containing the whole voltage drop across the reverse by Zener diode. Now where do we use? So VZ has a value which does not change too much, so we use it also as shunt regulator, which is we use it in parallel with the load, and what that does is gives us a very good control over the over the voltage that's applied to a load. So here's one more example of how we use it. The question states that we have a Zener diode whose nominal voltage is 6 volt at 5 amps. So if I it has an incremental resistance of RZ is 80 ohms, and what voltage do you expect if the diode current is half double? What is the value of VZ0 in the Zener model? So we have to see a few observations. So delta VZ is the similar way that we saw. This is RZ times delta IZ. So here the current IZ is given at 5 milliamps, and the question say what happens if it is halved. So RZ is still the same, and we can halve 5 milliamps, and now we have to use the minus value because it's in reverse bias. Minus 5 over 2, minus 5 milliamps. And that gives us minus 200 millivolt. Now, what would be the Zener voltage? We plug in into this relationship, and we get 6 minus 0.2, which is 5.8 volt. So this is the value when we make it half, the diode current half. The voltage goes from 6 to 5.8. The second part is doubled. So let's see what happens if the diode current is doubled. Same delta VZ is equal to RZ, and for delta IZ we are now going to use the double the amount. So 80 ohms times 5 milliamp is 400 millivolts. Now VZ is going to change by 6 plus 0.4, which is 6.4 volt. All right, so finally the question is the value of VZ naught that is obtained by using the model at zero current. So in that case, we would convert VZ naught from this relationship, and VZ0 is then VZ minus RZ IZ, which is 6 minus 80 ohms times 5 milliamps, what we just calculated, would be 5.6 volt. All right, very good. So as we talked about, we use it as a voltage regulator, and what it does is it gives us a stable output voltage even when the the current is changing by a big number, our output voltage is still very stable within a very small range change, and hence we can get a DC power supply that can drive a circuit without swaying too much, even if there is a change in the current.